new share instead of swapping. This thing was clowning on me. All right. Come on. Just connecting. There we go. All right. So we're going to jump right back into our reactions and jump back into this handout. I think the last thing we talked about was the Wittig reaction. Let me go back up. Yeah, we did. So we're going to finish the carbonyl reactions and start talking about the amine reactions today. And then for each example, we'll find a example in the handout. We'll work through some of those problems as well. So up top, we did the Wittig. We know that the Wittig is a way to convert carbonyl, aldehydes, and ketones into alkenes. Now we're going to talk about this reaction right here, which is actually uh, it's a fairly simple reaction, converting carbonyls into, or aldehydes or ketones into what we call hemiacetals or acetals. And if you'll notice, the reaction conditions is based on the product is based on the stoichiometry. If you take the aldehyde and you react it with 1 mole of an alcohol, doesn't matter what alcohol it is. I just use methanol, um, just as an example. But you got 1 mole of methanol and your ketone, you see you get what's called a hemiacetal. If you notice, it's the alkoxy group from the alcohol that's here that attack that carbonyl carbon. All right. It's a fairly simple mechanism. We're going to talk about that in a minute, but I just want to give you an overview first. And if you look at the second reaction, it's the same ketone, but this time, instead of 1 mole of alcohol, you got 2 moles of alcohol. All right. And you can see that reflected in the product. You see 2 of your alkoxy groups. And this is, I know I say this all the time, but this part is the alkoxy part, right? The alk is for the carbon chains.
Oh, nigga, these niggas in my grass and shit.
Oxy is for the oxygen. All right. So we're gonna look at this mechanism, how it works, and then we're gonna find some examples in the handout and work through them. I like doing it that way instead of just talking about the reactions and then at some other time applying them. We're gonna apply them right away. So let me move this out of the way, and then I'm going to cut this out and put it on a blank page so we can work through the mechanism. All right, let me paste it right here. All right, so let's take that hemiacetal reaction first. Let me put a date up here. Date is 7. So acetal, hemiacetal formation. Use a different pen too. All right, so when we talked about as we have talked about carbonyls, what is one of the qualities or characteristics of a carbonyl that we've kind of been harping on? like how as far as the way it reacts.
Illumination.
That's one thing, yeah. But okay, let me rephrase that question. If I had a carbonyl and I had it in the same flask with a nucleophile, what's going to happen with that carbonyl and that nucleophile?
Nucleophile gonna attack the carbonyl, right?
Going to get attacked, right? And so the alcohol in this case, and I'm changing up the ketone, but it's the same. It doesn't matter. The arrows are going to be the same. So the alcohol, that oxygen has lone pairs, so that's going to attack your carbonyl like so, right? When that happens, what's the common intermediate for all these carbonyl reactions when they get attacked by a nucleophile? What do we call that intermediate?
Tetrahedral.
Tetrahedral intermediate. It's the same for all carbonyl reactions. If they get attacked by a nucleophile, that carbonyl is going to form a tetrahedral intermediate that's going to eventually become some product. So now this is my intermediate. My electrons look sketchy, but it's cool. And then this is my nucleophile. Right, that's positive, that's negative. Now, how do I get from there to the hemiacetal? What do I need to do? Well, how do I get that negatively charged oxygen to become an OH? What can I do? Is there an H somewhere in that molecule that can be used to protonate that oxygen?
Yes.
Yeah. Thank you. Don't be scared to answer. Just answer because everybody's got their mics off. So after like 5 seconds, if nobody says something, go ahead and answer the question. It's okay. But yeah, there's a proton right there, right? And all I need to do is grab it and give those electrons in the OH bond to the positively charged oxygen. That's what do we call that process when we take a proton from some proton source?
Deprotonated.
Deprotonation or proton transfer, right? This just happens to be intramolecular, right? Intra just means it's happening within the same molecule. So intramolecular proton transfer is the last step in that mechanism, right? So we end with the hemiacetal. Are y'all following that? Any questions about that? It's just the first step is nucleophilic attack, and then the second step is that proton transfer. Right? That's how you get the hemiacetal. So it's a two-step mechanism.
I do have a
nucleophilic to get to your tetrahedral intermediate, and then the intermediate is normally going to do one or two things. It's either going to get protonated or it's going to eliminate. Those are the two processes that are possible with that tetrahedral intermediate. It's either because the first step is addition, right? So that tetrahedral intermediate, you're either going to trap it by adding a proton, which we just did, or it's going to eliminate and reform the pi bond and kick off some leaving group. In this case, it gets trapped through proton transfer. All right. So now when we talk about the acetal, the difference is that again, in the acetal, you got two alkoxy groups, right? And that's a consequence of the stoichiometry because you started with 2 moles of alcohol relative to 1 mole of your starting out ketone, right? But you don't start from the beginning. Like that goes through the hemiacetal first, and then it becomes the acetal. You don't have to go back all the way to the ketone and start from the beginning. 1 mole of alcohol is going to give you the hemiacetal, which is what we have here. All right, that's my hemiacetal. All right, so when I want to make the acetal, I'm going to start from the hemiacetal, right? Because I've already used up 1 mole of the alcohol to make the hemiacetal. Is that clear, or do we need to start at the beginning?
You said you were continuing to you were continuing from the product that was the hemiacetal.
Right.
Continue on making
Right.
that. Okay.
Yeah, and the reason I say that is because if we look at the reaction up there, it's 2 moles of alcohol. When I do the reaction with 1 of those moles of alcohol, I'm going to get the hemiacetal. So the second mole of alcohol is what's going to convert the hemiacetal into the acetal. Does that make sense? So that's why you get the acetal if you have 2 moles of alcohol. So let's just start at the acetal. So I'm gonna start here. So I have this, and let me put that up here, make it clear. All right, so the acetal forms from the hemiacetal, right? 1 mole of your alcohol is going to make the hemiacetal, and then the second mole is going to convert that into the acetal. So we're going to start here, and I'm going to run out of room. I already know it, but it's okay. I'm going to turn this around. First step is going to be proton transfer, right? Because what I want to do is make my OH a leaving group. All right, I want to make it the leaving group, and one of the ways to do that is to turn it into what?
You said turn into what?
Water.
Water. Like one of the ways to turn that leaving group of the OH into a better leaving group is to make it into water, like a hydronium. All right, so we're gonna do this. So we're gonna take a pair of electrons, pull off this proton right here. So we're gonna do proton transfer on that, right? And I'm gonna run out of room. Let me shrink that down some. Shrink all of this down. Can't do that on a whiteboard. I'll tell you what. When we go back to the classroom, I'm actually gonna miss this part. Let's see. Yeah. So we're here. So that's positive. The OCH3 is still here. So that's my intermediate plus.
But why is the OCH3 still on there for the? Oh, I guess because it's the intermediate.
It started there, right? It's right here too.
Yeah, but I'm saying because I thought you like knocked it off. That's what I was like saying. But I guess because it's the intermediate, it's still on there.
Yeah, and if we knock it off, then we're not going to get to here. We're trying to get here with 2 OCH3s on there. Right, so if we knock it off, then that'll defeat the purpose of trying to get to the product. Now here, in order to get to, sorry about that, to get to the product, we can go 2 routes. Right, we can lose water. I mean, you'll have a pretty stable cation at that carbon. So you can, right, that's the next step, to lose water. You can lose it by it just spontaneously leaving, You know, it's a good leaving group. You got a pretty stable carbon left behind, and you end up with this intermediate, this carbocation intermediate right here. That's positive, right? Or there's another way you can lose it too, and that's if the alkoxy group forces it out with a lone pair, and that'll leave you with this intermediate. But you'll have a pi bond there, and let me get this out of the way. I'll fix it later. You'll have a pi bond here, and then your oxygen is positive. Both of those pathways are plausible, right? That's one of the things about a mechanism is it's a proposed mechanism, right? And a proposal is just that, unless you do the actual experiments to prove that you know it's definitively this mechanism or this mechanism, then every mechanism is a proposal until you prove it. That's how that works. But either one of these pathways is plausible. So you can lose water spontaneously. So I'm gonna write that down here. If I can spell. Right? Or you can force that water out with the alkoxy group. That's what we call neighboring group participation. Don't get that confused with NMR now. That me calling a proton a neighbor is a colloquialism. It's not like, that's not really how you refer to it. It's just a way for me to help you to understand it. So don't get that, those two topics mixed up. So neighboring group participation. Right? Both of those methods are plausible. Both ways are plausible. So it's up to you. If you were proposing a mechanism, you can pick the way you like, the one that you like, right? I gotta add another page and move this because I don't want to. It's just running down. All right. So I'm gonna cut this, well, copy it, and then I'll fix it before I upload it. All right. So now what's left to make the acetal? What do I need to do? I just need to attack whichever intermediate I want to use with the OCH3. Am I right? Which one do y'all like best? The spontaneous loss or the neighboring group participation?
Spontaneous.
Okay, we can roll with that. So this is just going to attack here at that carbon, right? And then it'll give you, that'll leave you with your acetal. Right? Either one of those intermediates is fine, right? But the last step is nucleophilic attack. And if these reactions seem overwhelming, you always want to go back to like the basics. You want to boil it down to what you know. And you should know at this point, you should know the difference in a nucleophile and an electrophile and what they do, right? And so, and how they interact with each other, right? Nucleophiles interact with electrophiles by sharing electrons with them, right? So that, going back to the basics is all, you know, even though we are doing more advanced reactions, going back to the basics never hurts because the basics is that's your foundation. Uh-oh. Right, that's your foundation. That's why it's so important when you take in part one, not to try to skate through it. because you never stop seeing those concepts that you learn in part one. You're gonna see it over and over again. You're gonna see the same stuff in, some of you may have already noticed this if you're taking like cell and genetic, if you're taking animal phys, you're taking biochemistry, it's all the same concepts. Nucleophiles reacting with electrophiles, acids reacting with bases, right? Are any questions about the acetal or hemiacetal formation? All right. Let's start talking about amines. We can do that real quick. Let me go back up to here. I'm gonna just cut the thing. Just cut it. And then we'll discuss the amines first, and then we will. Sorry about that. Pull some problems from this worksheet and start working through some of those too, dealing with these topics. Where did that come from? All right. So with the amines, we got three reactions that we're learning here. Um, one of them is Amine synthesis. That's the top reaction. We're not going to go through the mechanism for that. This works. It's identical to esterification, right? You start with a carboxylic acid, and the nitrogen here is going to replace, wrong pen. The nitrogen on that carboxylic acid is going to replace the hydroxyl group. The nitrogen on the amine is going to replace the hydroxyl group. And you can do this with a primary or a secondary amine, right? If you watch that video, the discussion about amines, what's a primary amine, what's a secondary amine is in there. Can somebody tell me the difference between a primary and a secondary amine? You can discuss the amines in terms of how many groups are bound to it or how many hydrogens are bound to it. I think I heard somebody's mic unmute. Go ahead.
I was just
Isn't
gonna
it?
ask, like, if the nitrogen is like attached to one carbon, it'll be primary, or two carbons, it'll be secondary.
Secondary, good. So if you got a nitrogen with one substituent and two hydrogens, it's primary. And if by the same token, if you got a nitrogen that has two substituents and a hydrogen, I'm gonna put my long period, then it's gonna be secondary, right? Both of those work. Both of those work for amide formation. And it's, again, is similar to esterification. You start with a carboxylic acid, you take an amine, you mix them together, you warm them up, and then you do, it's just like transesterification. The only difference is what you're swapping out that a hydroxyl group with is an amine and not an alcohol. Right? You still do that same internal proton transfer, all of that. You can also use acid chlorides to make amines too, make amides too from amines, right? So that we don't have to go through the mechanism because we already seen the mechanism dealing with esterification, right? It's the exact same mechanism, just different atoms, taking place, participating. The second reaction is what we call imine formation or shifts base. And take some. All right, that's another name for imine. If you notice, the imine is this product right here. If you look at that product, you'll see again, you gotta be thinking about what's happening in this reaction. I'm taking the carbonyl, and this is the essence of the reaction. I'm going to replace oxygen in the carbonyl with the nitrogen from my amine. That's exactly what happened here. Right? Even if you don't know the mechanism, you can see what happened. You look at the starting materials and then you look at your product and you can see what happened. The oxygen in the carbonyl got replaced by the nitrogen of the amine. Now it's not that simple, but we're going to talk about how that works. I actually have a whole problem in this packet with the mechanism. We're just going to go through and put the arrows in because it's kind of counterproductive to write it out when we already got an example where we can just talk through it. All right. And then the second reaction, there's also a problem dealing with that too. So we're going to look at that as well. This is amine synthesis, right? This is called what we call Gabriel synthesis. Right? It's a way to make amines, primary or secondary amines. So you start with phthalimide, you start with an alkyl halide, and then treat that with potassium hydroxide, followed by water, and you end up with a primary amine. So we're going to talk about the mechanism for that in another example. All right. So let's look at the amine synthesis. Let me find the question, and then we can talk. It's right here. Boom. Perfect. All right, so let's talk through this mechanism, right? So you got a ketone and you have a primary amine. You're going to react those two together. The amine is your nucleophile, and then the ketone is your electrophile. That's if you need a way to start thinking about the mechanism and how to push the arrows, find the nucleophile, find the electrophile, and that'll dictate, how your arrows are applied, right? So how did we get from here to here? From the starting materials over here to this intermediate? How did we get there? What do you think?
Well, the nucleophile is gonna attack. Oh, okay. So can I try to annotate on the screen?
Go ahead. I hear the excitement in your voice. Please do.
Is it like that? I finished the annotating.
Yes. That's exactly what happens. So you attack the carbonyl carbon, you break the pi bond. Great. That's an addition reaction. Am I right?
Yeah.
Right. Most of your carbonyl reactions are gonna, well, not most, they all happen. If you're reacting with a nucleophile, they happen through addition. Right. So you do an addition reaction to get to this intermediate. Now I need to go from this intermediate to here. What do you think? We've seen this 3 times already today. You got a negatively charged oxygen. We put some electrons in here.
I think I know what happens.
Go ahead.
All right, I'm gonna just annotate on screen again.
Go ahead. You got a negatively charged oxygen and it's proximal to a proton, right? Good. Wrong, that's going the wrong direction. Look at the proton. The proton is positive. So you're not going to push electrons away from it. You're going to push electrons towards it. So just turn that arrow the opposite direction. But you're right. That's what's getting ready to happen right there. You're just going to steal a proton from the atom next door. Good.
Uh,
All right. You also have to remember that when you take that take that proton, you got to give that pair of electrons between N and H back to nitrogen. Just need to put a curved arrow in there, if you can fit it in.
wait, what did I forget? What did you say? Give something back to nitrogen.
Yeah, right here. Hold up, let me change pens. That pen is too thick. So that, right? Because it's a proton transfer. So when the oxygen pulls it, the NH bond is going to break, right? So you get those electrons back to nitrogen.
Okay.
Mm-hmm. But the first arrow was correct. Yeah, that was correct. All right, and then that gets us to here. Now you should already feel like something's brewing up, right? I need to get rid of OH, and I need a pi bond here. That's my product, a double bond to nitrogen, right? So how do I get rid of OH? We've seen this twice already. We're actually more than twice. We've seen it like 3 or 4 times since we started this section.
Wouldn't it just like when you kick it off, like the arrow will go towards it?
But it's not just going to leave though. I got to make it amenable to leaving. So I need to protonate it. You see the other intermediate with the 2 hydrogens? I need to make it into a hydronium. So how can I do that? Based on what you see now. You don't even have to guess about it, speculate. How can I go from here to here? Look at what you have and look at what you start with. Right? In that other intermediate, nitrogen has 2 lone pairs and it's missing the hydrogen. And then oxygen has 2 hydrogens and it's positive. So how can I do this from here? Intermolecularly, right? There's no other proton sources around or anything. So how can I get there?
Don't you just do another proton transfer?
Just do another proton transfer. That's exactly right. I just take a pair of electrons from here, and then I'm gonna put that back to there, and that'll get me to that intermediate.
Oh man, I should have asked to annotate. I literally was gonna do that.
That's all right. You got to check. You can do it on the handout. All right. Now I want to get to my product. What can I do? You've seen this 30 seconds ago when I had the hemiacetal and the water, and I need to force water out. What do we call that?
Elimination.
That's right. It's an elimination. And so the elimination is going to happen here, intramolecularly. So I'm going to push a pair of electrons here, boom, like that, and then boom, like that, and get rid of water. So I end up with my Schiff's base plus water. Notice the nitrogen now is naked or almost naked. It came in with 2 protons, but in order to make that pi bond, they had to lose both of those protons, right? So both of those protons went towards the formation of water as a leaving group. Now this is a long mechanism, but it's really the multiple steps repeated, right? The only 2 steps that are different are here, the elimination step and the addition step. But the other 2 steps are both proton transfers. All right. So that's the mechanism for making a shift base or imine. Addition, proton transfer, and then elimination, right? And then if you look at that intermediate that eliminated, it looks very similar to the intermediate that we saw before with that hemiacetal when we were getting ready to make the acetal from it, right? A lot of this stuff is similar. If you start recognizing those patterns, then the mechanisms, they kind of run together. Like, oh, this is the same type of process. Oh, it's just going to be an elimination. Oh, I have OH, and I know I need to get rid of it. If I protonate it, I can make it into water and get rid of it. So that's the thought process behind a lot of these things. If you look at this handout, we actually have well, we haven't finished this. We still got to do this reaction, but we can do that because we learned that reaction in part 1 actually. But we're gonna still do it. But okay, let's go right here. What's the product? Y'all like multiple choice, so what's the product of this reaction? You got 2 alcohols, right? 2 equivalents of ethanol and a ketone. And the reaction is labeled. So it's telling you what the product is. Can't be that.
Wouldn't it be? No.
Ooh, you know what? I forgot. Yesterday, somebody asked a question, and I was supposed to cash out them, but I forgot to get the cash out from the chat, and I have to go back and get that chat. Unless you want to put it back in there. I can't remember who it was though. But if I see the name, I'll know who it was.
It was me, but it's okay.
All right, yeah. Can you do that? I can do it right now while we're waiting on an answer.
I feel like it can't. Well, I feel like it's 1 because I feel like it's. Yeah, I just feel like it's 1.
Okay, here's the thing. You don't have to feel it. You can know it, right? Because it is 1. Because 1 is an acetal, is it not? That's the same thing that we just did up top, but instead of using methanol, we're using ethanol. We had that ketone. We started with this ketone, and then we added 2 equivalents of methanol. It's the same product. It's just a different structure. So you really you can know that when you look and see you got a ketone and 2 moles of alcohol. This is the part that's going to attack, right? Or this is the part of the alcohol that's going to end up attacking your ketone, right? And you see that right here. And because you got 2 moles of it, that's going to happen twice. So yeah, you're right. You're right that it's 1, but I want you to be more confident about how you know it's 1. Does that make sense?
Yes. It
Yeah.
does.
Yeah. But you're absolutely right. It is 1. It wouldn't be 3. 3 would be, in this case, the intermediate on the way to 1, because 3 is the hemiacetal. Right? 3 is the hemiacetal. So it's not 3. So
It
on an
can't.
exam, that's not a trick question or partial credit if you pick 3, because the stoichiometry is telling you that it's going to be 1 and not 3. If
Yeah.
that 2 was a 1, then it would be 3. All right. All right. Let's do let me see what else I want to do. 9 minutes left. We'll work on the epoxidation stuff on Monday. And we're gonna work on this page on Monday. Yeah, let's go ahead and do that Gabriel synthesis real quick. And then we're gonna work on this second half of this handout Monday. So this is the Gabriel synthesis. So the first, this is actually a synthesis too. So this is the amine that we're gonna make from Gabriel synthesis, right? So what this is asking in the blank is what is the alkyl halide that was used to make that amine? And I'm gonna show you how to like think about this retrosynthetically. So it's asking you what alkyl halide was used. All right, so here's the phthalimate. And the reason why it's negative, hold up, let me send this right quick so I don't forget again. So I'd like to keep my word. Uh-oh. Come on, Russell. One second. All right. So the phthalimate, remember, these are the reagents. So it's phthalimate. I'm just rewriting this. So that's phthalimate, right? And if I treat that with KOH, it's actually going to remove this proton. So you end up with this right here, plus water, right? Are y'all following that? So you got N, that's going to be negative, K is positive, and then plus water. That's the outcome of that reaction. That's why you need the KOH in there, right? So the phthalimate plus KOH will give you this. And then what happens is the nitrogen attacks whatever alkyl halide you use, right? So what it's asking, when it's asking for here, like the amine is the final product, but you have to start with an alkyl halide in order to get to the amine. So what happens with the alkyl halide, if you just have an alkyl halide like that, just an SN2 substitution. So this comes in and attacks like so, and you end up with an intermediate that looks like this, where the alkyl halide part, the alkyl part of the alkyl halide is bonded to phthalimate. And then that's why you need the second step that just pops that ring open. So it pops open that phthalimate ring and releases the amine, right? So what if I'm asking you here what to put in this block right here, what you're looking at is replacing or swapping out nitrogen with a halogen, either bromine or iodine. Those are going to be your most reactive halogens, right? So your alkyl halide will look like this. I'll just start with a bromine or bromide. Right, so when you do, and let me go back up, when you do Gabriel synthesis, I have it, cut it, I cut it. Yeah, right here. So when you do Gabriel synthesis, that's what you do. You take phthalimate, you deprotonate it with KOH, and then you do a SN2 type reaction on the alkyl halide. And then that intermediate, you can pop it open to give you this plus whatever your amine is. So we'll come back to that, but I want to finish that problem, because what happens now once I get the amine, and I'll clean all this up before I post it. I'm gonna put this mechanism up top. right? What happens between that amine, that primary amine, and that ketone? What happened up here when I had a primary amine reacting with a carbonyl? Not a carboxylic acid now, but a ketone or aldehyde. Right here. What kind of reaction was that? Is it not an amine formation or shift base formation? If I take a primary amine and react it with an aldehyde or a ketone. So down here, well, I'm right here, right here. Down here, what should the product of that be? Like what happens in that reaction?